Thank you. So this is a joint work with a bunch of people. There's a nice story about this, which I'll hopefully get to soon. It's also helpful to have paid attention to Seth's talks, but not necessary. Okay? No offense. Okay, so I'm actually going to start from a string matching problem. I like strings and the problems that arise in string matching. And particularly we'll be talking about a virus detection problem. So imagine you have a router and you have a lot of data going through the router and you want to detect viruses. Typically, what network intrusion detection systems use are digital signatures. And what they do is within the router, they search within the streaming data, they search for digital signatures to alert, intrusion alert, someone's trying to do something bad to the system. Okay? And a bottleneck that reappears in the industry that's trying to deal with this problem is what I like to call gap signatures. So what does this mean? So viruses don't necessarily, digital signatures or viruses don't necessarily appear in a consecutive area in the stream of data. They might appear scattered throughout the stream. And the other issue is that we have to report viruses as soon as they appear, right? We don't want to say, oh, yesterday there was a virus in the stream. That might be too late, right? So we want to report them as soon as we see them. Here's a virus. Okay. So one way of visualizing this is, let's say this is some text or a stream of data that's coming through, and we might have some of the digital signature over here, and a little bit later we might have the other part of the digital signature, and we somehow want to be able to express that, we found this digital signature. So in order to be able to do this in this streaming model, we need some method of so-called remembering what happened in the past. What has appeared in the past, maybe a long time ago, right? And know that these things are connected somehow and these comprise a digital signature. Okay, to make things even worse is that reality has some serious constraints. This is true for many aspects in life and here as well. So text is streaming very, very fast. We want to react very quickly to each character or each other new packet or character or however you want to look at this. And we cannot use a lot of space in the streaming model or in real life also, right? We have routers that have limited amount of space usage, which is a constraint on the system. Okay, so this is can be formulated as a streaming problem. I'll mention a few more things. So if you look at the actual digital signatures that NIDS, network intrusion detection systems, try to detect, about 95% of them only have one gap. So what I mean by one gap, so a gap pattern is the following form. It has two subpatterns, P1 and P2. And we're going to put a special symbol over here, which is going to be the gap symbol, that says, this symbol matches any substring of any length, even zero-length substring. Okay, and now we can give a model of this problem as an algorithmic problem. So we call this the online dictionary matching with one gap, or the ODMOG problem. It sounds like a name of something from Harry Potter. Where we want to pre-process D gap patterns. Each pattern has just one gap. And given an online text, one character at a time, we want to be able to report matches of these gap patterns as soon as they appear. We don't want to wait, like we said before. We want to report them as soon as they appear. Okay, so this is the ODMOG problem. There's a bit of a story time now. Okay, so this was just some theoretical, some background, but let's talk about a story. So the motivation of this line of research was actually we were approached by some company whose name I won't mention about this problem from the industry. And they were telling us, this is a real problem. How do we solve this? Can you help us out? Do you have some ideas from theory? Maybe you guys can, you guys work a lot on string problems, so maybe you can help us figuring how to solve this problem. So we did come up with some solutions, and the solutions either had a lot of space, which was not practical, so they're not interesting, or they could use low space, but required square root of D time per character. So D is the number of gap patterns. And the number of gap patterns is really, really large. Square root of D is huge. This is not something that we're willing to accept and practice. All right, so this is not good. Okay, so
really, really large is 1,000 or 1,000,000 or 5?
Tens of thousands. There are a lot of viruses up there. So the question is this necessary, right? Like, okay, we work really hard. We can't seem to beat the square root of D. Is this really necessary in some way? Can we prove a lower bound? And the answer turned out to be yes. At the same time, we're working on some threesome problems, and we noticed, we've proved some reductions showing that if you commit square root of d, then you can solve threesome faster than quadratic time. Okay, so this is really bad news for practical aspects of the problem. So maybe we can still somehow do better in practice. And turns out that, yes, we can do better in practice. So the threesome lower bound instance is dense. This touches a bit of what Seth spoke about earlier. But real data is actually sparse. And we came up with a new algorithm where the cost per character depends on the some sparseness measurement. We'll talk about this later, of the input. Right? So for sparse cases, we can actually do things very, very quickly. Okay. And then a natural question to ask, well, can we do better than the sparsity measurement? Or is the sparsity measurement somehow necessary? And again, the answer is yes. And again, we show a reduction, a lower bound from threesome, showing that for any input, any graph, any family of graphs with this specific sparsity, there are instances where solving them faster than just the sparsity time would solve threesome faster than quadratic time. Okay, so it looks pretty positive, right? Lots of yeses. So the rest of the talk is really going to eventually reach triangle enumeration problems, and we're going to be talking about upper and lower bounds for these, and this all relates back to this ODMOG problem, online dictionary matching with one gap. Okay, so unfortunately, the ODMOG problem has some other inherent difficulties that come from the fact that it's a string problem. You know, some subpatterns might be suffixes or prefixes of some other subpatterns, and you have to somehow deal with these things happening at the same time. So we're going to simplify at least this presentation today. I'm going to be focusing on a simplified version of this problem, which can actually be viewed as a graph problem. So this is what I like to call the induced subgraph problem. So we're given an input, a graph G, and we want to preprocess it so that afterwards we're given a set of vertices, k vertices, we can quickly output all the edges induced by this list of vertices or set of vertices. So for example, we might have this graph over here, and we can preprocess this graph. And then if we're given these queries, these black vertices, then we'll output these 4 edges. All right, these are the edges induced by these black vertices. Okay. So I'm going to show you now, hopefully show how if we have a solution for ODMOG, then we can solve the induced subgraph. It's a very simple reduction. So for each vertex in the graph, we'll create a character. And for each edge uv in the graph, we'll create 2 gapped patterns, u star v and v star u. And here's an example. So this is a graph from before. So you can see, for example, for the edge DE over here, we created these 2 patterns over here. And this is a set of patterns that we're going to preprocess using an algorithm for ODMOG. Okay? Just believe me that this covers everything. Okay, and now, so this is the first part of the reduction. Then, how to reduce a query. So given a set of vertices v1 through vk, we'll create a text with just the characters v1 through vk. And we'll look for this text, for all the patterns within this text. So again, in this example, if this is a query that we had before, these black vertices, then we can create this text over here and output these specific patterns, which correspond exactly to these specific edges, which are exactly the output of the induced subgraph problem. The reason, of course, we create 2 patterns for each edge is to deal with directions, right? Okay, so clearly ODMOG solves induced subgraph. So for the rest of the talk, I'm going to focus just on the induced subgraph problem, mentioning, you know, with some more algorithmic techniques, we can also solve ODMOG with comparable running times. But let's just focus on the induced subgraph because it's easier to reason about. And one more thing is that in the induced subgraph problem, the input is a set of vertices. So now we're going just to assume that it's a list of vertices, and the vertices arrive one by one. So we're turning it into an online sort of problem. Yes?
In the original motivation, is it the case that you would have the bidirectional thing with
No, but you can overcome this by creating a bipartite graph and creating some order. Okay. All right, so just to, this will be helpful a little bit for later. So I'll show you now a very simple, there are several algorithms that obtain square root of d that I mentioned before, which is square root of m, the number of edges in the graph over here, using techniques that date back to the 70s. There's nothing really exciting about this, but they give some insight as to what's going on a little bit later. So we'll say, so this is a solution for the induced subgraph problem. We'll say a vertex is heavy if it has at least square root of m neighbors and light otherwise. And for each of the heavy vertices, we'll maintain some list of all of the light neighbors that have appeared in the current query of the induced subgraph. Right? So for a vertex v that arrive, we first mark it that has arrived. And if it is light, then we're going to scan all of its neighbors. Doesn't have a lot of neighbors. We can afford to do that. And we'll check if they're marked as well. If they're marked as well, we list appropriate edges. Also, if our neighbors, if a neighbor v is heavy, then we add v to the list. This list over here, we add v to the list of neighbors that have appeared for the neighbor. Okay. If v is heavy, then we have this list of all these neighbors that have already appeared. We just output them. That's easy. And we also scan the most square root of m heavy neighbors that v might have, right? The most square root of m, since the number of heavy vertices is bounded by square root of m. You kind of have at most m over square root of m heavy vertices in total in the graph. So the total runtime of this is just going to be a bunch of square root of m's and the size of the output, which might be really large because of this part over here. Okay, simple algorithm, nothing too exciting about this. Okay, and again, like I mentioned before, this algorithm plus some more algorithmic techniques. Also, you can solve ODMOG in similar runtimes. So the question is, can we do better? And there are two answers. One is no and one is yes. No, because of a three-sum lower bound, showing that you have to spend square root of m time for the induced subgraph problem, assuming linear preprocessing. And yes, if we use some beta parameters, which goes back to the sparsity measurements that I mentioned before. So let's first talk about the three-sum lower bound, and I'll just give a quick recap of what set intersection is. So set disjoint is, first of all, like Seth mentioned before, we're given a family of sets F. The total size is capital N. We have q pairs of sets that we want to decide for each pair of sets if they intersect or not, if the sets are disjoint or not. Now remember, this is very important to remember, this is an offline problem. Right? We don't receive the queries one at a time. We receive all the queries as one batch together with the input and want to solve everything at once. Okay. The version of set intersection problems that I'm going to be using right now is set intersection. So we want to enumerate the output, not just decide if two sets intersect, but look at the intersection and enumerate all of the elements in the intersection. This turns out to be very, very useful. And again, recapping some of what Seth said in the previous talk. So we showed that for offline set intersection, with an instance size, so, right, we have these two parameters, delta and gamma, but an input size, capital N. So the lowercase n here is the three-sum n, and the capital N is the instance of the set intersection. Okay, that's important to realize. So the instance size is lowercase n to the 3 plus delta minus gamma over 2. The query size is, the number of queries that we want to answer is n to the 1 plus gamma. The size of the output is n to the 2 minus delta, and we get this lower bound. And you don't have to really absorb this now. This is just to remember what the, so capital N, Q, and T are parameters that we might care about. Okay. Something which is helpful, maybe intuitively, is to notice that gamma controls the sparsity of the inputs. Okay. For some meaning of sparsity, for some definition of sparsity. Interestingly, over here we can actually take gamma to equal 0 in this case, as opposed to the set disjointness case that Seth spoke about earlier, where it has to be strictly larger than 0. And delta controls the output size, right? N to the 2 minus delta. So larger gamma means more sparse, and larger delta means less elements in the output. Okay. All right. So we'll take a graph representation of the set intersection problem. So we have some sets here in A, some sets here in C. Might be the same sets. And we'll do the natural, we'll add natural, so we have here all the elements in the universe have vertices for them as well. And we'll do the natural thing of connecting each set with all of the elements within the set, both from A and from C. So this is a quick social experiment. Who sees the Starship Enterprise here? Okay, we got a winner. If you tilt your head to the right a bit. No? Yeah, okay. Anyway, so we have these sets over here and the sets over here connected to the elements over here. And queries are just edges, if we're interested in some queries, so we can add edges between A and C corresponding to the set intersection queries that we want to be able to answer. Now in our case from using the threesome hard instances, we get that the number of edges over here is exactly the number of queries, which is n to the 1 plus gamma. The number of edges over here between this part and this part is this term over here. And the size of the output is going to be n to the 2 minus delta. Right? Just reminding you again. So one thing that we can quickly realize is that if we consider this edge over here and look at all of the triangles that contain this edge, this corresponds exactly to all of the elements in the intersection of these two sets. Right? That's easy to reason about. Okay. So in general, if we could enumerate all the triangles in this graph, we could solve this offline set intersection problem. Right? So let's talk about triangle enumeration and see what we can say about it. So the triangle enumeration problem is we're given a graph with m edges and we want to enumerate all the triangles. Okay? And a theorem that I'm going to quickly prove right now is that Italian-Rodé's algorithm from 78, which takes m as the number of edges to the 1.5 time, is essentially optimal. Meaning that we don't expect an m to the 1.49999 algorithm. Okay? So essentially optimal means ignoring all sub-polynomial factors. Okay, so if we take gamma to tend towards 0, gamma to tends towards a third and delta to tends towards 0, then we'll get that the size of our instance here, the number of edges over here is going to be n to the 4/3. The number of edges over here between A and C is going to be n to the 4/3. The size of the output is also going to be n to the 4/3. Things work out very nicely. And now we see that, well, if the number of edges is n to the 4/3, and I have to spend n squared time to enumerate all the triangles because this eventually solves threesome, then we have to spend m to the 1.5 time in total in terms of the number of edges. Right? N to the 4/3. So we have to spend n to the 2/3, which is square root of m time for each one of the edges. Okay. Another interesting thing to point out here is that the time per triangle in this case turns out to be square root of m. Same reasoning. The number of triangles in the graph is n to the 4/3, so we need to spend n to the 2/3, which is square root of m time per triangle. This is in contrast to Michal Petrascu's result, where he showed from the threesome conjecture that you have to spend m to the 3rd time. So this is slightly higher lower bound, which is great. Okay. So we've spoken about this offline problem of triangle enumeration, and we kind of understand, okay, there is some optimal algorithm. We can also consider two data structure versions of triangle enumeration problems. So one is an edge triangles query and one's a vertex triangle query. Let's see what they mean. So in an edge triangle query, this is what I mentioned earlier. We want to pre-process a graph. This is a data structure problem now, okay? It's an online problem. We pre-process the graph so that given an edge, we can quickly enumerate all the triangles containing this specific edge. Okay? So I think it's very natural to see that this solves set intersection. Right? You can actually show that both of these problems are equivalent, completely equivalent. There are two waves reduction, so it's not difficult at all. So these are edge triangles queries. What I think is interesting to consider is the vertex triangles queries. So here it's somewhat of a complement problem. We're given a vertex, enumerate all the triangles containing this vertex. Okay? So these are two natural types of queries. So what can we say about them? So like I mentioned already, edge triangle queries are equivalent to set intersection, and they're the typical way of showing conditional lower bounds for enumeration problems from threesome. In general, when we talk about conditional lower bounds, not just from threesome, but also from Boolean matrix multiplication or orthogonal, some way of looking at orthogonal vectors, or also looking at online matrix vector. So all these problems kind of go down to asking a similar question about, edge triangles queries. But what I want to talk about today is focus more on vertex triangles queries. And there's some sense, like we said, a complement of set intersection. And interpretation is that we consider a specific element in the universe, and we want to enumerate all the queries for which this specific element is part of the output. Right? And this doesn't seem to fit nicely with other popular conjectures, maybe with one exception. So it seems like we really need threesome to be able to say something about this because of the offline problem that we considered before. And we'll see soon how this helps us. Okay, so let's show a lower bound for vertex triangle queries. Of course, it's going to be based on the offline problem of enumerating all triangles, right? You can always solve the offline problem of enumerating all triangles by answering vertex triangle queries on each one of the vertices over here. Right, we can solve threesome this way. Okay, so again, we're going to take gamma to be tending towards a third, slightly larger, and delta is going to be tending towards 0. And the number of vertex triangle queries is going to be the size of the universe. So if you do the math, the size of the universe comes out to be n to the 2/3. Okay, and this means that either the pre-processing time has to be the time it takes to enumerate all triangles anyway, just enumerate all triangles and prepare all the answers in advance, or the query time has to spend, well, this is the number of queries, then each one of these queries has to spend n to the 4/3 time, which is exactly the number of edges, right? Which basically means that a query will cost linear time, right? That's also trivial. Right, so one of these trivial things has to happen, which is quite unfortunate for these type of queries. Okay, so let's see how this helps us onwards. So let's just, actually before that, let's recap quickly what we've said so far. So we've basically claimed that threesome reduces to offline set intersection, which reduces to triangle enumeration, which reduces to vertex triangle data structure. And the conclusion is that either the pre-processing time needs to be m to the 1.5, or a query time needs to be linear m. Okay, so what I'm going to show you next is that, and this connects us back to what we said before, is that a vertex triangle data structure is reduced to induced subgraph, and then we can say something about induced subgraph and also ODMOG. Okay, so how do we do this? This is also not too difficult. So we pre-process a graph for induced subgraph queries, and now we want to use this data structure for induced subgraph queries to answer vertex triangles queries. So what we do is when we want to answer a query on a vertex V, we just input all the neighbors of V into the induced subgraph data structure. And there's a clear bijection between the edges in the output and triangles that contain V. Right? If there's a triangle between two of my neighbors, if there's an edge between two of my neighbors, then that has to be a triangle. Okay, and this works backwards as well. Okay, so what kind of lower bound do we get from this simple reduction? So let's say D is a degree of V. Then either the pre-processing time is still the same as it was before, pre-process all the possible, m to the 1.5 time, or the query time. So previously for the induced subgraph problem was m over, for the vertex triangles problem, it was just m plus order of p, plus the size of the output. Over here we have to divide by d, since this is an amount of time that we spend per vertex in the induced subgraph problem. So, and there are d vertices, so we're going to have to spend m over d time. Right, the lower bound is reduced by d. Okay, so the natural question to ask is, well, how big is d? Right, the larger d is, the worse it is for us, because we get a weaker lower bound. So let's look back at our graph, and if we look at the number of edges and we divide by the number of vertices, we get that the average degree is going to be m to the 0.5. Okay, and if we plug this back in over here, then we're going to get a square root of m lower bound for a query time for each vertex, right? Which translates to square root of d for the ODMOG problem, for the string virus detection problem. Okay, so this seems like pretty bad news, at least if you're interested in practical algorithms. Right? After all these reductions, we get this lower bound, and the natural question to ask is, why is this happening? Why do we get this lower bound? Why? What's this, other than just reducing it from threesome, is there anything else that we can hang on to say, maybe we can do better? And if you look a little bit carefully, the graph instances that give the square root of m lower bound are very, very dense, and in practice, the graphs are very, very sparse. In particular for virus detection, they're very, very sparse. So we would like to find some other algorithm, whose runtime depends on sparsity, and of course doesn't contradict the threesome lower bound. Okay, and is there one? Well, the answer is yes. So now we're going to talk a little bit about an upper bound. And the upper bound uses orientations. So open parentheses. So orientations, the orientation problem is we're given an undirected graph as input, and we want to output a directed graph. And the goal of by orienting the edges. And the goal is to have a low out degree. So for example, the out degree of this node over here, this vertex over here is going to be 3. The in degree might be very, very large, but the goal is to have a really small out degree. The maximum out degree should be as small as possible. Okay? So a very natural term which is relevant to orientation problems is the arboricity of a graph. So the arboricity of a graph is the smallest number of forests into which the set of edges can be partitioned into, spanning forests. And it's also closely related to other sparsity measurements like the graph degeneracy or the strength or the width and pseudo-arboricity as well. So if you've seen any of these, they're basically up to constant factors all the same. And there's also, Nash-Williams proved that the arboricity is also, it's another natural way of looking at it, the density of the most dense subgraph, densest subgraph. There's a -1 here that has to do with the fact that it's forest, but if you just ignore this -1 to get intuition, you consider all possible subgraphs and you look at the number of edges divided by the number of vertices, and the densest subgraph defines the arboricity of the graph. Okay. And arboricity shows up in a lot of applications, so there are a lot of well-known bounded graphs of, well-known bounded arboricity graphs, like all forests, planar graphs, graphs with excluded minor can all be shown to have a constant arboricity. There's no really dense area in the graph. Okay, and how's this related to orientations? Well, just going back, right? So the arboricity is the smallest number of forests into which E can be partitioned. So let's say we somehow find this partitioning into forests. We could orient each forest to have out degree 1. Just for each connected component, which is a tree, pick one of the vertices to be the root, and orient all of the edges towards the root. Right? So the out degree is going to be at most 1, and then we just merge all the oriented forests together, so the out degree is going to be at most the arboricity. Okay? And there's so this is a little bit difficult to do because finding partitions efficiently seems hard to do. At least we don't know. I should be careful about seems hard to do. We don't know to do it faster than something like cubic time. But there are linear time algorithms obtaining a 2 approximation. Okay, so the maximum out degree of every vertex is going to be at most twice the arboricity. Okay? And now we can talk about the upper bound for this induced subgraph problem. So each vertex maintains the, I should say, we orient the graph using this order of alpha g out degree orientation. And now we do the following. So each vertex is going to maintain a list of all of its incoming neighbors that have already appeared, similar to the heavy nodes, heavy vertices in the previous algorithm. Now when a vertex v arrives, then we first list all the edges of vertices in the list, right? If any of my incoming neighbors have already appeared, they should let me know that they have appeared somehow. So I just list this as part of my output. And then we scan outgoing edges, right? We have the most order of alpha g edges to scan, and we output what's needed to be outputted. Okay, so the total time is going to be order of the arboricity plus the size of the output. Right, and this is really great news because in practice, the arboricity is really, really low. Okay, so what do we know about the induced subgraph problem now? Well, if we assume linear preprocessing, we have an upper bound of order of the arboricity and a lower bound of order omega square root of m from the threesome conjecture. And how the two coexist? Well, it's easy to prove that the arboricity is always the most square root of m. So for really, really, really dense graphs, yes, this is the lower bound, right? One of the things that I don't like about lower bounds is that they seem to hide some of where the difficulty really lies, right? So it's enough for one point of the function to be a lower bound to say that this function is a lower bound, right? So this is a lower bound, but it's lower bound only because in the dense case it's a lower bound, but for sparse cases it might not be. And sometimes just by looking at the function and claiming this function is a lower bound, we hide what's really going on behind the function. So what we can actually prove is, I'll just summarize this in words, that if we can do faster than this, alpha g to the, say, 1 minus epsilon, then for any alpha g, for any dependency of alpha on the number of edges in the graph, then we could solve, then this will refute the threesome conjecture. Right, so what we managed to also show is that this is also the best we can do for any sparsity, any polynomial sparsity. Right, so you don't have special algorithms for really dense cases, which was clear from before, or really sparse cases, maybe do something even faster. Okay? And this ties up with another line of work. So we show that a bunch of other triangle enumeration problems are also optimal. So I mentioned before the Itairo-Days algorithm from 78 to the m to the 1.5 is essentially optimal. Chiba and Ishizeki showed an algorithm that runs an order of m times the arboricity of the graph, and we actually managed to improve this a little bit by shaving some log factors recently. This is with Seth Petty and Eli Parat. And there's also a recent paper by Bjorklund, Pei, Virginia, Williams, and Uri Tsvi, where they showed an output-sensitive algorithm for listing only T triangles. This is a type of runtime that they get, assuming that the matrix multiplication constant is 2. And we also managed to show this is essentially optimal. Now, this was actually not possible to show from the three-sum conjecture using Michal Petrosky's ideas, because you kind of get stuck over here and you can't say anything about this part. Okay. So the conclusion of this is, we managed to show an efficient solution for induced subgraph, which also leads to an efficient solution for Vertex-Triangle queries, which is optimal. And on the one hand, and also we can extend these ideas to solve ODMOG efficiently on practical inputs with some more algorithmic machinery. And I think this is really a great example of how understanding theory and understanding where the difficulty comes from ends up leading to practical algorithms. We also managed to show that a bunch of offline triangle enumeration algorithms are essentially optimal. And we spoke about vertex triangles, but as Seth mentioned, we have an unpublished result that shows that edge triangle queries, we have an upper bound that meets the lower bound as well for the entire spectrum, assuming the three-sum conjecture. So basically, it seems like, at least as far as three-sum is concerned, we know a lot about triangle enumeration problems. From, things are pretty much tight, up to subpolynomial factors. Okay, so I guess the one open question that I keep getting back to is, okay, so great. So we know from the three-sum conjecture that these things are hard. It's hard to do better. But maybe you can use other popular conjectures to show lower bounds for vertex triangles or for induced subgraph. And let me point out where I see the difficulty being, if you're want to think about this, to give you, well, maybe you don't want to listen to me, but might just get in the way, right? But so a vertex triangle query has a flavor of an outer product, right? If you look at matrix multiplication, if you consider set intersection as multiplying two matrices, where one matrix is sets and elements, and the other matrix is elements and sets, then vertex triangle queries in some sense correspond to outer products. Okay? But the known popular, the known conditional lower bound techniques that we use, maybe related problems, don't seem to suffice because they're really about inner products. So there seems to be this gap between what we know. We know how to say things about inner products, which really correspond to set disjointness queries or set intersection queries. And it'd be really nice to somehow relate these outer products into these problems as well. Okay. Yeah, that's it. Thank you.
We have lots of time for questions.
So you mentioned that you gave a conditional lower bound for triangle enumeration of omega 1 to the m to the 1.5, assuming the three-sum conjecture, right? But I wonder what is known just combinatorially about the maximum number of triangles in a graph with n nodes and m edges.
It's at most m to the 1.5, a clique, for example.
Yeah, but if that, in the worst case you have that number, then that would be an unconditional lower bound.
Right. So one thing which I maybe should have emphasized more is that the conditional lower bounds are not because of the number of triangles. The number of triangles is polynomially less than the conditional lower bound that we get. If you recall, it's a long way going back, but since we have time anyway. When we look at the set intersection problem, Here we go. The size of the output has to be polynomially less than n squared in order for all of these lower bounds to make sense. Right? If the size of the output is somehow n squared, then just enumerating all the elements and all the intersections is going to cost n squared, and like you say, you get a trivial lower bound.
N squared also the number of edges?
So the number of edges is strictly less than n squared as well. You can somehow reason about that.
M to the 3 halves. It's possible that in your application, m to the 3 halves is larger than the number of triangles. Is that what you're saying?
No, because you can always show that the number of triangles is also at most m times the arboricity of the graph. Right? So for each query that you ask, you have to spend at most the arboricity. That's
the general statement look like, why conditional while there's an unconditional?
Yes. So yeah, but what's going on over here is that we have this gap over here, which is the number of triangles or the size of the output is polynomial less than the lower bound.
The number of triangles is smaller than.
Right. It is possible that the lower bound really is the amount of time that you need to spend per triangle, and not the rest of the stuff. Right. So you have in a query, a lot of queries have this some set amount of time that you have to spend for the query, and then each element in the output you have to spend some time reporting it. So it's possible that a lower bound is actually on the amount of time you have to spend on reporting a query, which in this case would be n to the delta, and not on the on the reporting, which would be n to the delta, and not on the query part, the set query amount of time you spend per query. So maybe you can spend much less than square root of m, but the time, if you spend a lot of time on the output, almost there. Right, maybe over here it should be constant and it should be output times something as a lower bound.
So you mentioned something about towards the end about the outer product versus inner product thing. So is there a concrete question regarding some version of the outer product problem that you can formulate or state?
I don't have one. I'm looking for one. Right? That's yeah. I mean, one way of looking at this is that you can solve BMM by performing a Boolean matrix multiplication by computing the outer product of each one of the elements in the universe. And then you get n squared matrices, and you have to spend you get n matrices, each of size n squared, which is the output of each one of these outer products, and then you have to somehow to add them all together, right? So just this computational time means you get nothing from the reduction. Just the amount of computation that you do to perform the reduction is already n cubed, right? That's the only place where I saw some connection to outer products. Other problems don't seem to really give. Maybe QES, you could do something, quadratic equation systems, but
They might have been resolved. It's no longer believed.
no longer believed to be hard. Okay, so never mind.